So hi, welcome to the Project Explain Newton's Laws of Motion and Forces video. So today we're going to be talking about Unit 2 from the AP Physics C and Mechanics Course and Exam Design curriculum, which is Newton's Laws of Motion, basically everything covering dynamics, forces, accelerations, friction, tension, and the like. So the very first thing that we need to discuss is what is a force, and we need to be able to describe that. So a force is a vector quantity, okay? So that means that it has a magnitude and a direction. And which in an isolated system, meaning if there's only one force acting on the system, it results in the system accelerating. Also, forces in an inertial reference frame, which means that the reference frame is not accelerating. So in most cases, that means that the reference frame is not moving at all, or it's moving with constant velocity, are governed by Newton's laws of motion. In non-inertial reference frames, there are other forces that we have to consider called fictitious forces, namely like translational forces, Coriolis force, azimuthal force. But in AP Physics C mechanics, you don't need to worry about those. All of your reference frames are going to be inertial for your calculations. So first of all, we're going to look at Newton's laws of motion. So you might be already familiar with them from previous science courses, and they are pretty much what govern most of the motion in our universe. The first law is that an object's motion will not change unless acted upon by a net force. So that means that there has to be a net force. So there are many scenarios where there may be two forces or three forces or four forces acting on a system, but they will all be canceling each other out. So the net force is zero, which in practicality is the same thing as if there were no forces acting on it when it comes to acceleration. So basically, if there's no net force acting on a system, its motion will not change. So if it was initially at rest, it will stay at rest. If it was moving initially with some velocity, its velocity vector will remain the same. So that means it'll be traveling in the same direction with a constant speed, which was the same as it initially was. The second law is probably the most famous law, arguably, in all of physics, which is F net, or the net force, the vector sum of all of the different force vectors that are acting on the system is equal to the mass times the acceleration vector. So keep in mind that these are vectors here, thus the bold, which means that we have to consider different directions. They're not scalars. And third, every action has an equal and opposite reaction. So if I push on you, you're also pushing back on me, right? So that's part of, if you push really hard on a wall, right, you feel the wall pushing back on you. That's part of the reason why it's so dangerous if you run into a wall or if you fall from a large height and hit the ground, because you are hitting the ground with a large your momentum is very large, which means that there's a large impulse, which means that the force that is being exerted on you is large, and likewise the force that you are exerting on the ground is large. We'll talk a lot more about momentum and impulse and different things like that, changes in momentum, collisions, in Unit 4, which is all about systems of particles and linear momentum, but that's another application that you should be aware of from regular physics. So we're going to be looking at our first example, which is a pretty simple one. So they're asking us to find the net force on the system in unit vector notation. Okay, so once again, we need to acknowledge that these are vector quantities. So we either have to convert everything into unit vector notation and then sum them, or we need to look at the x and y components of each of the forces separately, sum them, and then we can get our final answer, which is what I am going to do. So the sum of the forces in the x direction. So let's look first. So we have this 4 Newton force, which only has a horizontal component, so that's easy. That's just 4. And then minus, we have this force, which is 8 newtons, but at 60 degrees to the horizontal. So its horizontal component will be 8 times the cosine of 60. Hopefully you remember that from trigonometry. So 4 minus 8 cosine of 60 degrees is equal to 4. The cosine of 60 is 1/2. So that would be 8 times 1/2 is 4. So 4 minus 4 is 0 newtons. So it's actually in equilibrium in the horizontal direction. And then for the y component, sum of the force in the y direction, we only have one force that only has a component in the y direction. That would be 4 square root 3 newtons downwards. The direction, so you can arbitrarily choose a direction to be positive or negative. In this case, I'll choose upward to be positive and to the right to be positive on the x-axis, because that's what you may be familiar with from math. But if you do it the other way around, as long as you're consistent with your signs and your directions and making sure that they are correlative to each other, everything will work out in the end. So the vertical component of F2 is just 8 sine 60 degrees minus F3, which is 4 square root 3, which 8 times the square root of 3 over 2 minus 4 square root of 3, we also get 0. So this object is in equilibrium. Or actually, to be more precise, I should really say translational equilibrium. Right, so that means that there's no linear acceleration to it. Right now, that's not very important to specify, but once you get to Unit 7, which is all about torque and rotational motion, there's a difference between translational equilibrium and true equilibrium. True equilibrium is achieved when there's no translational or rotational motion. So just start getting used to that distinction. And like I mentioned earlier, make sure that you're remembering to do the vector sum. You can't treat them as scalars. So Newton's third law is basically all about the classification of internal and external forces. So internal forces are the forces that bodies in a system exchange with each other, but they can't actually accelerate the center of mass of the system because they cancel each other out. So in the example of me pushing on the wall, if we consider the system to be me and the wall together, then the normal force between me and the wall would be internal, because the force of me pushing on the wall and the wall pushing back on me, they're reactionary to each other and they cancel each other out, right? So that's something that is really important to consider. So internal forces, basically whatever forces you consider to be internal, depends on the system that you choose to look at. And external forces are forces applied by something outside of the system that we choose and do have the capability to accelerate the center of mass. So in this diagram over here, we want to look at the internal and external forces. So whenever they ask you about internal forces, the first thing that you need to think about is, what is the system? And right now, the system is all three of these blocks together. So if you accelerate 3 blocks together, each one is going to push on the other, right? So there would be, if I label them as 1, 2, 3, there would be the force of 1 on 2, the force of 2 on 1, the force of 2 on 3, and the force of 3 on 2. However, if we consider this whole thing to be the system, those are internal forces, those normal forces between the blocks, because they're equal in magnitude, opposite in direction, they're canceling each other out if we consider all 3 blocks together as the system. The only force here that is external to the 3-block system is this force F. So if we were trying to look at the acceleration of the system, what we look at is, per Newton's second law, the sum of the forces is equal to the mass times the acceleration. We sum all of the external forces. Technically, you could also sum the internal forces, but that becomes irrelevant because they all end up canceling out, so there's no need for that extra step. So the net external force on this system is just F. And when we're looking at the acceleration, all the objects in the system are going to accelerate with the same acceleration in this case, because one block isn't going to quantum tunnel through the other block and suddenly magically have a different acceleration. So you kind of need to use your critical reasoning skills in that case. And in AP Physics and Mechanics, almost all of the systems you're going to be dealing with, they're mainly going to have the same acceleration. There are some special Atwood's machines where you have multiple pulleys attached to each other where the accelerations may be different, where you have to use some trickier methods to get the acceleration for each mass, but we're not going to worry about that right now. So you have to take the net external force, which is F, and then consider the total mass of the system. So that'd be the mass of 1 plus the mass of 2 plus mass of 3 times the acceleration, and then you can just solve for the acceleration, right? So that's a method that we're going to employ very, very frequently in order to solve our problems in forces. So some important forces that you should know are the tension force, which is the force applied by rope. And normally, almost always, I've never seen a problem where this wasn't true. We consider these to be massless, and the tension, and thus the tension is the same everywhere. If they were not massless, it would vary because the amount of weight that certain parts of the rope would be holding would be different if the rope had mass, right? But because our cords are massless, we don't have to worry about that. Another thing to note is that tension, when it's the only force acting on an object, always acts along the direction of the rope. That's another really important thing that you should remember. So if there's a problem where, for example, if you have kind of a setup where you have two ropes connecting to a mass, and then you cut one of the ropes, so the X indicating the rope that's cut, the other rope, its tension will drop to balance the component of gravity that's along in the same direction as the actual rope itself. So in this case, that would be mg cosine theta if we consider this angle here to be theta. That's something you'll look at more actually when you do simple harmonic motion problems, but that's just something that you could be asked as a conceptual question. The normal force, the force applied by the ground or other solid surface on a mass, and it's always perpendicular to the surface. That's why it's called normal meaning perpendicular. And it's a reactionary force, like I mentioned earlier, and it's equivalent to the magnitude of the perpendicular component of the force that's applied to the surface. So that is important when we look at inclined planes, because if you have a mass m, which has weight mg, obviously, the normal force is only going to balance the component mg cosine theta, which is perpendicular to the surface. That's something really important to remember. And the gravitational force, pretty obvious, near Earth's surface. The gravitational force is mg, where g is approximately 9.8 meters per second squared. We'll get to tension in literally 3 or 4 minutes right now, so don't worry about that too much in the first few examples. We'll come back to that, because friction, there are different kinds of friction, which we're going to talk about, namely kinetic and static. So let's do some example problems. So for this one, what is a normal force? So what we need to do is just sum the forces in the y direction. So I'm going to once again consider the positive y to be positive. So we have the normal force in our free body diagram, n, and then we have F, which is at a certain angle beta, right? And then we also have mg. And just a note that in your free body diagrams, always make sure you draw the actual forces and not components. That's important for FRQ questions. You don't want to lose points just because you accidentally drew components instead of the actual force vectors. Just keep that in mind. You can always draw a separate diagram on the side for your own reference with the components, since that's usually a lot more useful, but the technical definition of a free body diagram is one that shows the actual force vectors acting on the object. So in this case, we have n minus mg, obviously, and then we have the y component of the force vector F. So that would be F sine beta, just from this triangle that we can draw here, right? So this would be, the horizontal would be F cosine beta, and then this would be F sine beta, and it's in the negative direction, thus the negative sign, same as gravity, and it's equal to 0 because it's in equilibrium in the horizontal direction, or in the vertical direction at least, because it's not burrowing into the ground. So then from here, it's just simple algebra, and we get n is equal to mg plus F sine beta, which would be A in this multiple choice question. So for example number 3, it says in the system on the left, what is the force the mass 4m, so this guy, exerts on the mass m? It got cut off, but that's what it says. And we know that the surface is frictionless, so friction doesn't matter. So as in a lot of other problems, with systems, like I mentioned earlier, the first thing we're going to do is find the acceleration of the system. So sum of the forces is equal to the mass times the acceleration. So the acceleration is the sum of the forces over the mass total of the system. So the only force that's external to this 4-block system is F over here. So that would be F divided by the total mass of the system, which would be m plus 2m plus 4m plus m, which is 8m. Okay, so then what we need to do is we need to change our view of the system and look exclusively at this block. So if we look only at that block, we have a force, which is the force of this 4m block, the normal force, pushing this single m block forward. So I'll say the force of 4 on 1. Okay? So the force of 4 on 1 is basically the only force that's acting on it, not basically, is the only force acting on it in the horizontal direction, which is what is accelerating that block. So we're going to set up a Newton's second law for that block. So in this case, the force of 4 on 1 is just equal to this guy's mass, which is m, times the acceleration, which we already found earlier, which is f by 8m, which should be equal to f by 8. So answer C. And that should conceptually make sense that it's only f by 8 because this mass, 4m, is only pushing this one block forward, right? Whereas this force F is pushing all 4 blocks forward, thus the magnitude is bigger. So make sure you're always doing those conceptual checks to make sure that you actually understand conceptually, at a conceptual level, what's happening. Okay, so friction, yay! So there are 2 types of friction, namely static, when the object's relative velocity is 0. So this is important to consider. So if the objects could be moving, and there are many scenarios where they are, but if their relative velocity is 0, meaning they have the same velocity, or they're moving with same initial velocity with the same acceleration, they're at rest with each other. Relative velocity is 0, and we consider it as static friction. Kinetic is there is relative velocity between them, right? So one is moving relative to the other. So you need to remember what the reference frame actually is in order to determine whether it's static or kinetic. So for kinetic, pretty simple. It's just the coefficient of kinetic friction, mu k times n. So the kinetic friction is always a constant value, okay? Static friction is a little bit more confusing. So the force of friction static is less than or equal to mu s times n. So basically what that means is the force of friction static max is the coefficient of static friction times by the normal force, but it doesn't necessarily have to be that value. It could be less. The static friction only counteracts the force which is being applied, and it obviously resists the motion, right? So if the force of friction static max is 3 newtons, let's say, but I'm only applying a force of 1 newton in the horizontal direction, the force of friction static that is actually occurring in that scenario, in that system, is only 1 newton because it's not moving, right? So it wouldn't make sense if 3 newtons was being applied because then it would be accelerating in the opposite direction. So in example 4, they're asking that the system is at rest, so the mass isn't moving, and the magnitude of the frictional force is mu s mg cosine theta. So basically, mu s times by the normal force, as you should know for an inclined plane. And they're asking, is that true, false, or we don't know? So based on what I said, you should know that the answer is we don't know, right? It could be at that max value. It might not be at the max value, right? So in this scenario, all we know truly is that the force of friction static is equal to mg sine theta because it's balancing that horizontal component of gravity, but we don't know what it is in relation to the coefficient of static friction and this formula over here. So unless they tell you that the maximum amount of static friction has been achieved, or if any more force was applied, it would slip, or things like that, you can't use the Fs is equal to mu s times n formula. If they use that language, then that's when you apply that formula. Okay, so now we're just going to do a ton more practice problem solving. And this will help you apply all the kind of nitty gritties that we've just gone through with all the different types of forces, Newton's laws, and friction, obviously. So first example that we're going to do is what is the acceleration of the system above if m is much larger than little m and the coefficient of kinetic friction is mu. And obviously the string is massless and the pulley is also massless and frictionless. So like in all of our other problems, first we need to identify the internal and external forces. So on this mass, there's the normal force, there's the, I'm just going to draw components right now. This isn't a free body diagram like I mentioned earlier, but for time's sake, I'm not going to draw a free body diagram and then a separate component diagram. So you have the horizontal component of gravity, the vertical components of gravity. You also have the frictional force, and since it's kinetic, we just apply that formula, mu times by n, so mu mg cosine theta. And we get n because we know it's in vertical equilibrium, so n is equal to mg cosine theta. And we also have this tension force. And for the little mass, we just have the tension force, and we have mg. But the tension, we're not going to worry about it because it's an internal force, right? So we know that the m is much bigger than little m, so the acceleration is going to be in this direction. So I'm going to consider positive to be in the direction of the acceleration, okay? So for our net force equation, we know that the sum of the external forces acting on the system is equal to the mass times the acceleration. So A is equal to the sum of the forces over the mass total of the system. So the net force basically is big mg sine theta, because that's in the direction of the acceleration, minus mu mg, big mg, cosine theta, minus little mg, divided by m plus little m. And that is option D. So for all these problems, as you can see, the problem-solving approach is pretty similar. You find the acceleration first, and then if they ask additional questions after that, you set up more net force equations, substitute your acceleration in, and get the answer. Okay, it's a very classic problem. It's an elevator problem. So basically, we know that the 50 kilogram student is standing on the elevator, and we know that the elevator is accelerating downward at 1 meters per second squared. So for the sake of this problem, I'm going to establish downwards as positive. The velocity is irrelevant in these types of problems. So I'm going to quickly draw a quick sketch. So we have our student who's standing there. The forces acting on them is the normal force and the gravitational force. So for some of the forces in the y direction, that would be equal to may, and once again, downward I'm considering as positive. So mg minus n is equal to ma. So then we just need to substitute our values in. So the mass is 50. I'm going to consider g as 10 for this, which you often can do in multiple choice questions. Minus n is equal to 50, his mass again, and the acceleration, which was given to us over here. And then it's just simple algebra, and we know that n is equal to 450 newtons. So that is a very classic type of problem where you have to identify which direction it's accelerating in to find what a scale would read. And the weight that a scale reads is not the gravitational force, it is the normal force. Just like if you have a spring scale or like a hanging type of scale, the weight that it records is the tension, not the actual gravitational force. So just as a conceptual check, if it's moving downwards, you should record, or your answer should be smaller than the actual weight of the person. If it's moving upward, it should be greater, because that normal force is either smaller or bigger to adjust for the direction that the person is accelerating in. So B in this case. So we have a couple more problems to go through. So this is a very classic kind of setup we have for a multiple choice question, where they're giving you a graph and then you need to kind of relate that to the behavior of another graph. So this is a velocity versus time graph that they've given to us, and they want us to kind of predict how the force to time graph would look like. So we know that force is equal to mass times acceleration, right? And we also know that acceleration is equal to the derivative of the velocity, right? M is just a number, so it doesn't change the behavior of the graph at all. So in this case, we've been given the velocity versus time graph. So in order to relate that to the force graph, we need to look at its derivative. And the derivative of the velocity versus time graph, which is the acceleration graph, will have the same behavior as the force graph. So in this case, we have a cubic for just looking at its behavior for the velocity graph. So the derivative of a cubic is a quadratic, right? So that would be the acceleration, and the acceleration will have the same behavior as the force graph, just from Newton's second law. So based on that, we know that the answer is C. Okay, here is our last problem. It is probably the most complex of them all because it has pretty much everything. Complex Newton's third law applications, action reactions, internal forces, friction in there as well. And we're looking at the acceleration again. So for this one, what I'm actually going to do is I'm going to draw each mass separately. So we have little m, and then we have big M, and we'll do each one of them at a time. So on little m, what we have is the normal force of it going up, right? And then we have its gravitational force, mg cosine theta and the y component, and then mg sine theta and the horizontal component, right? We have tension. We know it's going to be moving down like this in that direction because m is much bigger than little m, so the frictional force would be backwards like this. The frictional force is kinetic, so we can apply our formula for mu k times by n. And another thing to note is that it also has the normal force of m, or big M, on it, pushing down, right? So n1 has to counteract both mg cosine theta and n2. But for this problem, that doesn't matter. If there was friction on the incline, we would have to consider that. But it says that the incline itself is frictionless, so we don't need to worry about that for this problem. But there is friction between the masses, okay? So there is friction between the masses. So on big M, there's mg cosine theta, tension in this direction. Once again, the force of friction, kinetic, opposing motion, and then you have mg sine theta, and then you have the normal force, N2. So what we need to look at now are the external forces. So actually, in this case, the only external forces are gravity, specifically the horizontal components, and friction, right? Because the normal forces in the vertical direction are canceling each other out because it's in vertical equilibrium. It's not burrowing into the incline. And the tension forces are canceling each other out. At first glance, you might say, oh, wow, the tension forces, they're both in the same direction, so they're not internal. But we need to consider the direction of motion because we're looking at the movement of the system along the direction of the acceleration. So in this, while it's going up, the direction of acceleration is upward. So the tension for this mass is technically in the positive direction, whereas for the top mass, it's going in the opposite direction as the direction of acceleration. So this tension force is going in the negative direction. So they're canceling each other out still. So it is an internal force. So our only external forces are gravity, specifically in the x direction, and friction. So we're just going to do the same thing. We're going to do our net force equation. So sum of forces is equal to max, and we consider the total mass and the sum of the net external forces. So I'm gonna consider it being in the direction of the acceleration as positive. So we have big mg sine theta minus little mg sine theta minus 2 mu mg cosine theta divided by m plus m. Note that it's 2 because that frictional force is acting on both of the masses because you have that action-reaction, right? Newton's third law. That's important to note in there. And we're getting 2 mu mg cosine theta because the normal force of N2, which is the one that's determining the friction, because it's friction between the blocks, is just equal to big mg cosine theta, because once again, it's in vertical equilibrium. And this is our answer, which is choice C. Note that choice A is a trap because it specifically says that the incline itself is frictionless, and just at first glance, this answer choice is accounting for friction on the incline. That's what this addition here is. Okay, so that's pretty much everything you need to know for forces. So obviously, the next unit we're going to be doing is work, energy, and power. So we're going to learn about different kinds of simple machines, work and energy, conservation of work and energy, gravitational potential energy, and all those different things which are kind of like forces, foundational for the rest of mechanics, AP Physics C mechanics. So we hope that you will be prepared for all your in-class assessments and really understand the concepts of forces, and also excited to continue with work, energy, and power. So like and subscribe. Project Explained out.